Okay, hi. Thank you for attending my talk today. My name is Thor Anderson. I'm a PhD student at the University of California, San Diego. I woke up early this morning in San Diego, California, and drove all the way here, so you'll forgive me if so the title of my talk is Weight Design of Distributed Approximate Newton Methods for Constrained Optimization, which is a pretty loaded title. We'll get into sort of each element of what that means. And this is a joint work with my collaborators, Qingyao Cheng, who's a postdoc in our lab, and my advisor, Sonia Martinez. So this is the structure of the talk today. I'll start out with some quick motivation about the problem and then introduce the economic dispatch problem that we're looking to solve. And then we'll get into this distributed approximate Newton thing. What does that mean? Why is it approximate? How can you distribute the thing? We'll talk about that. Point 4 here, I think, is the most interesting part of the talk, although unfortunately I won't have a whole lot of time to dive into the technical details of it. But sort of this idea of designing weights over a communication graph for a second order method. How do you formulate that? And then we'll get into some simulations and wrap up the talk. Okay, so of course probably many of you are familiar with this, but I'll do the due diligence on the motivation, which is that renewable energy, such as solar and wind, is becoming more and more pervasive in our power grid. And that introduces a lot of engineering challenges, in part due to the decentralized nature of the distributed resources, as opposed to traditional bulk generation on clean energy. And also that there's many generators, which is tricky to handle from a dispatch perspective. So independent service operators are running an optimization every 15 minutes to compute power flows and keep the lights on. And so we're interested in optimization methods that can solve these trickier problems faster. And so the optimization perspective of this is, I would sort of contrast this with a traditional first order gradient-based method. I like to think of these gradient methods as a little bit greedy. You're essentially just going in the direction of the level sets wherever you're at in terms of your decision variable. And you sort of ignorantly take a step and you may, if you get unlucky, bounce around. Whereas a Newton method, which utilizes second order information of the cost function, is a little bit better in terms of it accounts for this curvature of these level sets more intelligently. And so again, we'll get into, well, okay, there's methods for designing communication edge weights for first order methods. What would that look like for a second order method? And of course, this has application in general network systems. I'm going to propose a pretty specific economic dispatch, but this resource allocation problem shows up in many areas of engineering. Okay, so what is the economic dispatch problem? Here is the full problem sort of formulated in the centralized fashion. We have a scenario of n generators who are attempting to satisfy a load for minimal cost. So we'll just have n separable local convex cost functions, and they each have their local decision variable, x sub I. And then they have maybe some local box constraints also, but the thing that's coupling the problem together is this global network constraint. Some of the states need to equal some value. So the states in this case can be thought of as power generation for each generator. And then of course this little d variable here can be thought of as a load that we need to meet at a certain time. And so we want to do that in sort of an optimal sense. So how do we formulate this for a manner that's well suited for a distributed algorithm? Well, we'll assume we have an undirected and connected communication graph. So we have symmetric Laplacian matrix, which is defined like this. And we're going to utilize the null space of that graph Laplacian. So we'll introduce an initial condition, which is feasible with respect to that global network constraint. Just a quick note on this, if you don't have a feasible initial condition, there are distributed ways to handle that. One of my colleagues, Ashish Chirukuri, has written about that, so not a big deal, but for now, for the purposes of this, we'll assume we're feasible. And now, consider stepping in the image of L by a new variable z. So if we update our state x, then we'll just write it out like this, x sub 0 plus lz is our new variable. Let's check that we're still feasible. Sum of the elements of x is of course the same as multiplying by the vector of all ones, and then the null space cancels out, we're good. Okay, so this is then the distributed reformulation of economic dispatch. This is equivalent to the problem that I just showed you before, where now I've sort of redefined the cost function in terms of z instead this time and rewritten the box constraints a little bit. And we'll adopt an assumption on our cost functions. This is pretty standard in literature, that their local Hessians need to be lower and upper bounded in some sense. That'll come in handy later. Okay, so what is this distributed approximate Newton thing? What's going on here? Well, unconstrained Newton for just a centralized problem, just think of the most classical thing, is defined like this. So we have on the far right side here the gradient, and you're weighting it by the inverse of the Hessian function. And so the interpretation for this is if you're at a certain point and you take a look at the curve of your function, and you instead take a second order Taylor approximation of that function, so you draw a parabola that best approximates it around that point, then this step solves that Taylor approximation exactly. So that's sort of the second order flavor of what's going on here. And then the classical algorithm updates x in discrete time with some step size. So if we wanted to approach this for just our centralized problem, we could, well, for now let's ignore the box constraints, we could rewrite one of the states in terms of this global constraint here. So now we have an optimization over only n-1 variables. But you'll notice here, if we take the Hessian of this cost function, it may be fully populated, or even if it was sparse, unless it's diagonal, if a sparse matrix, its inverse is not necessarily sparse. And sparsity is what we would want for a distributed algorithm. So you need global information to sort of implement traditional Newton in this case. So what are we going to do? Let's think about it from our distributed perspective. So consider P, which is our distributed problem, and take the Hessian now in Z instead. And just apply some chain rule here, and then we're evaluating, I'm defining this H just for shorthand of the original Hessian, of the original cost. And so, first of all, let me point out that this LHL matrix is not invertible. That's actually not a big deal. There's one eigenvalue of it that's fixed at 0. Just the equality constraint coming around. There's just some linear algebra to show why this is not a huge issue. So we need some notion of an inverse of this guy. So we're going to employ this Taylor series expansion, which for some matrix A, whose eigenvalues are bounded such that identity minus A is contained in the unit ball, then you can see the terms of this infinite sum here are shrinking, and that approaches A inverse. So we're going to use that. So let's assume for now that our non-fixed eigenvalues, and by that I mean the n-1, we have the one of LHL that's fixed at 0, so think about the n-1, and let's say they're contained in the unit ball. We'll talk about that later. Then we can define this sort of inverse Hessian thing that looks like an inverse Hessian at least, if you squint closely enough and turn your head sideways. And we'll call it approximate because we don't want to compute infinite terms of this sum. We'll just compute it up to the qth term. And this can actually be done recursively in practice. You can compute these terms by additional 2-hop communications. And so then to handle the box constraints, we're going to write out the Lagrangian of our problem. And so I'm defining here the constraint functions, which I've defined as this PZ. And then we introduce the Lagrange multiplier lambda. And now we want a saddle point of this function. That's the point we're looking for. And so I'm going to propose that we'll do a approximate Newton descent in the primal variable z here, and a gradient ascent in the dual variable. So this top step here requires information of your 2q plus 1 neighbors. Again, that can be done sort of recursively via 2 neighbor hops in practice. And this lambda has some non-smooth projection dynamics. So what I've defined here is this sort of bracket plus thing. Essentially all that means is lambda can't go below 0. If lambda is at 0, then this projection, if it were to take, these dynamics were to take lambda into negative territory, it just projects the value of that element to 0. So that's non-smooth, which is kind of ugly, but not actually a big deal. That's what's going on here. So this is our algorithm. This is how we're going to solve our problem. And of course, we've proven that it works, so you don't have to take my word for it. So again, the assumptions I think I've already stated. We have a feasible initial condition, connected undirected graph. and a Laplacian such that our eigenvalues are squeezed. I'm now characterizing how tightly we squeeze them by this epsilon, and that will come into play in a little while. And then we'll also assume that each agent knows his own and his neighbor's cost functions just so that he can perform the computations that he needs to. Great, so what happens? Then we converge asymptotically to the optimizer by these dynamics that I've given you. In our convergence argument, you can see that there's a very direct relationship between how tightly we've squeezed these eigenvalues, or if you just crank Q up big enough, the interpretation of either of these is that our approximation becomes good faster. So the rate improves if either of those is the case. And then if we relax the box constraints, we can actually implement this in discrete time with a fixed step size, and the convergence rate ends up being exponential, also characterized by this epsilon and Q. And so the keys to that, you have to be a little clever about how you choose your Lyapunov function, just because we have this weird approximate Newton weighting that's going on, but that brings us to Z star. Apply some LaSalle principle and reason with KKT conditions, it gets you to lambda star. These projection dynamics, a colleague of mine, again, Shishira Curry, worked on this and showed that there's a simple trick that you can use to sort of get rid of that, so it's not a big deal. And then the convergence element of this is you examine the modes of this identity minus LHL, and you can rewrite some of the modes that are going on here in terms of a geometric series in epsilon and Q. And that gives you your sort of analytic expressions for what the dynamics look like. Okay, so what's going on here with this weight design stuff? I've been asking you to take my word for it so far that we can squeeze these eigenvalues characterized by epsilon. But how do we actually do that? What does it look like? There's a lot going on here. I may just briefly go through this. Essentially, all I'm doing is saying LHL is an n by n matrix, but it has that one eigenvalue fixed at 0. That's kind of nasty. I don't want to have to deal with that. So I'm just going to change the coordinates, shrink it down to n minus 1 by n minus 1. And then I'll define a new matrix, M of x. And the reason it's a function of x is because H may be a function of x. And M is an n by 1 by n minus 1 by n minus 1 matrix, whose eigenvalues it shares with the other n minus 1 non-fixed eigenvalues of LHL. And again, this is changing in x, but think about just fixing x for now. We have design authority over the elements of L, and so we can wiggle around these eigenvalues if we're clever enough about it. So what does that look like? This is the second order weight design problem that's going on here. So this is sort of standard. You can see we're trying to shrink this epsilon as much as possible. And we have M is sort of lower and upper bounded by the thing. And then notice again, this is an optimization in L. M is bilinear in L. So that's one issue, but let's not think about that yet. For now, this is just a bit hard because we have M as a function of x over all real x. How do we deal with that? Well, that was why I made the assumption earlier. So there's an easy way to handle this. We can sort of rewrite H in terms of the lower and upper bounds here, rewrite M, and then we have an equivalent problem here, or at least a conservative version at the worst, to eliminate this X here. So now you can see 1B and 1C. These LMIs are the same thing as sort of this top LMI from over here. And then the same constraints on L. And so the good news, this can be solved offline. If you get some solution L star from this problem, then that can be implemented as long as you don't change the cost functions. You could change the constraints online if you need to, but if the costs stay the same, then your L star will still be optimal for those costs. The con is that actually both 1B and 1C are bilinear in L. 1B is not a big deal. It ends up being convex, and you can apply Schur complement and take care of that. So that's fine, but 1C is a little trickier. So we developed an approximation which is loosely based on completing the square in terms of handling that, and you can sort of reformulate it as an LMI in L, and that gets taken care of. It works pretty well. And another silver lining is we can guarantee that we can get you an epsilon that's strictly less than 1. And to see that, you can sort of reason with, if you were to just scale L by some scalar, you can look at the way that the eigenvalues of 1B and 1C evolve and see that that's true. Okay, so some simulations here, and then I can wrap it up. You may have to squint to see some of these trajectories here, but what I've done is I've taken a 3-state problem and projected it onto the plane that's orthogonal to the all ones vector, just so we can look at it in nice 2 dimensions. And these are the trajectories for varying Q. Now, one thing I'll point out here is if Q is even, the trajectories are qualitatively different than if Q is odd. And there's a very particular reason for that. I would have to dive into some technical details to tell you why. But what we find is that Q even on a whole is quote unquote better than choosing Q odd. And so that spills out of the convergence argument, but I'll sort of just tease you with that for now. So Q is the number of terms of the Taylor series expansion that we're using to estimate. Okay. And then we have some convergence here. So you can also see that the even Qs are converging. I'm just plotting the energy of the primal state and the dual variable here. And this is non-monotonic, and that's because I haven't given you the clever Lyapunov function that we chose. If you are a little bit smarter about your Lyapunov function, you see monotonic convergence. And so now, what's going on with this weight design stuff? Why is this so cool? Well, let's forget about the box constraints for now. This is just going to be only the global network constraint problem. And so I told you earlier that this converges exponentially. And so let's compare this to distributed gradient, both an unweighted distributed gradient and using a weighting method that's found in the literature. And what we find is, this is really cool if you ask me, that Q equals 0, which is analogous to a gradient method, converges faster just by virtue of having weighted the network with this second order information. So we designed L intelligently using the second order information, and then we implement something that's analogous to a gradient method, and we do better than weighted distributed gradient. And in this case, you don't see this weird phenomenon with the Q odd versus Q even. That spills out sort of from the box constraint, so you actually do better and better if you just crank up Q in this relaxed case. Great. So here are some open problems. I'm pretty sure that we can just discretize this algorithm if you're clever about the way that you choose your step size. For sure, a fixed step size won't work for the full problem. And I haven't done the dirty work on the analysis of this yet. It's tricky due to this projection that we have in lambda. It's a lot nicer in continuous time than if you were to discretize it. But this is a common choice of step sizes in the literature for problems of this structure. So I would want to give this a try. Of course, we can explore other methods of solving this bilinear weight design thing. I've just sort of developed a method that works well for our problem. But there may be some more due diligence to do on that. And then we want to adapt this weight design problem to topology design. So if I say instead of you can wiggle around the weights, but the network is fixed, what if the network is not fixed? How do you think about that? And there's a lot of literature out there on that. So we're working on a particular version of that problem. And then lastly, I gave you a very specific problem here. But I'm interested in formulating this second order weight design thing for more general problems. And my initial thoughts on that are it depends largely on what the global coupling aspect of the problem is in terms of how you can actually formulate these weight design problems. So in this case, it was pretty simple. Everything was separable except for this global constraint, and then we sort of eliminated that via L. It formulated to some nice clean thing here, but how can you do that if the network constraint is more general? So thank you for your attention. Thank you to ARPA-E for funding me, and of course my collaborators, and I'll take any questions.
We have time for a question while the next speaker comes up. Yeah, Michael.
So I'm a little bit confused actually by your comments towards the end of the talk. So you said the second order method was dramatically better than the gradient. But in this case, you don't have box constraints. You can establish exponential convergence even actually for first order method. You can just pass gradient to your objective function to graph Laplacian. If you design edge weights of the graph Laplacian, you're going to have exponential convergence as well.
Sure, yep.
So what is the meaning of your statement?
So yes, you will get exponential even with gradient without the box, as you say. What I would contend is the rate of this convergence actually improves. First of all, forget about the weighting. But if you apply a Newton method, you can see why the rate improves for more terms of this Taylor expansion. And then the other thing that I emphasized on this was that I think the weight design has some impact on an analogous gradient method. That was sort of why I claimed that our Q equals 0 is better than this distributed gradient weighting. But yeah, you're correct that the gradient is exponential. Does that answer the question?
So what can you say about rate of convergence in the presence of box constraints? Do you have any results?
Yeah, sorry?
Box constraints, do you have any results?
Yes, but it's trickier. So we have an expression for V dot over V, and you can reason with sort of the terms in that expression and show that, to give you a short answer, gradient is sometimes, if you're in the right part of the space, can actually be faster than Newton. Newton is smarter because it accounts for this curvature more. So in gradient, you'll see these oscillations a lot of the time. So this may be a fast part of convergence, but now we're doing poorly on it. Newton, the way that these terms in the V dot over V look, you can justify that this is more uniform over the whole space, that you'll have the same